Hey guys, welcome back to another video on weekly paper review. I know I missed a few weeks. There have been a lot of papers on multimodal modeling, which I plan to get to. So in this video, I've got 3 papers that I want to give overview of, and they might be 2 weeks old. So in the next videos, I'll try to catch up as much as I can. So the first video that we're going to talk about, or rather discuss about, is this two-stage backpropagation one. This paper is an optimization paper where the authors try to optimize the compute time or the computation of the backpropagation step. So this is not a theoretical paper, but rather it is it's a paper on how do you efficiently train models. So just to give you a rough idea of the kind of optimization that these guys do. So if you know what pipeline parallelism is, in pipeline parallelism, your model is split over multiple GPUs. That means, let's say if you have 4 GPUs and your model has 4 layers, you can split your model in 4 parts, give each GPU a layer. So for example, here, let's say there are 4 GPUs, so the model is split into 4 parts. And when we do a forward pass, forward is computed on the first GPU, and the activations are passed on to the second one, which does it forward, and then to the next one, and to the next one. And then backward passes take place. So that's your standard, a naive parallelism, pipeline parallelism. Now, obviously, this is not satisfactory because it creates these idle times. To avoid those idle times, what people do is people do micro batching using this gpipe technique, where multiple micro batches are passed in different orders so that you reduce these bubble times as much as possible. Now, this paper is about the backward pass. So once the forward is done, we will start doing the backward pass. And now backward pass, the authors say, has 2 components. One is the derivative of loss with respect to activations, and the other one is derivative with respect to the weights. So each backward computation can be broken up into this these 2 computations, P1 and P2, what they say, B1 and B2. And naively, it is done in this manner. B1 is computed first, and then B2, and then so on, B1 and B2 for the different GPUs. Here the authors optimize this process, and they say, you know what, when you compute B1, you can send the results to the next GPU so that it can start computing its B1. So this will reduce your backpropagation time by roughly half. And let me quickly talk about what those, like, why are we able to split this backward propagation in 2 steps. So 3 Blue 1 Brown has a nice paper, or rather nice page, overviewing what backpropagation is. But I will quickly go over the key idea here. So first of all, backpropagation is just basically the derivative with respect to your scalar loss function. So derivative of your scalar loss function with respect to the weights, so that you can, move your weights in whichever direction you want to move. And obviously this requires chain rule. I highly advise, if you're not familiar with the details of backpropagation, or if you've forgotten them, I highly recommend you go through this nice blog. But I will quickly summarize the key idea here. And before I even summarize the idea, let me tell you what a forward pass looks like. So the weights of the previous activation, or rather the previous activations, so for each layer, you get activations from the previous layer, which is A. The weights of the current layer and the biases of the current layer, they combine in a matrix multiplication, W times A plus B. This gives you the output of that layer. The same thing you do so here the previous layer came, and then you get the fully connected layer output, matrix multiplication Z, you apply some activation, you get A. So then that is passed to the next layer again. So here in lth layer, you get the previous layer's activations, you apply the weights to it and biases to it to get the output of this layer, apply activation, and then compute loss. This is what the forward pass looks like. So let me show you in terms of equations. So here you can see the output of the current layer is multiplication of the weights of the current layer times the activations of the previous layer plus the biases. And then you get the activations of current layer by applying your nonlinear thing. And so this is what it looks like, the whole thing. Now, when you compute derivatives, you will have to apply chain rule. So if I wanted to compute derivatives with respect to derivatives of my loss, see here is the loss with respect to the weights of a particular layer, you apply the chain rule. So what are the factors in the chain rule? So you first, and the way you apply chain rule is by you go node by node. So what goes into computation of C0? It's A. So that's why you first take the derivative of the loss with respect to the activation of lth layer. So this conveys how much does that nudge change C0. Then A is a function of Z. So that's why Z being the output of the matmul plus biases. So you take that derivative. And then finally, Z, you take the derivative of Z with respect to the weights. So this is the chain rule. And now, now as we go on to different layers, according to chain rule, you also have to, because the inputs are coming from previous layers and the outputs go on to the next layer. So in backward pass, you have to keep compounding the derivatives that are coming from end. So in forward, you go from beginning to the end. In backward, you go from end to the beginning. You keep on compounding the derivatives that you encounter at later layers. Not going into the details of backprop because that's not what the video is about, but let me quickly show you the equation. So first of all, this is the derivative of, let me zoom in a bit. This is the derivative of loss with respect to activations of, let's say, layer L-1, and that depends on the derivative of activations of layer L. And then according to chain rule, some other factors. So the key thing here is activation at any layer, or rather derivative of loss with respect to the activation at any layer requires the same for the next layer, coming from the next layer, or the end layers. So this is the derivative of loss with respect to the activations. Now, if I want to compute the derivation of loss with respect to the weights, applying chain rule, this is the equation we get. We can, so this is complete chain rule. I don't want to, again, go into details of it, but if you see here, the last three terms are purely the derivative of loss with respect to activations of the previous layer times a multiplicative factor like the other derivatives. So this derivative with respect to weights can be computed by multiplying the derivative with respect to activations times some other factors. Okay, so that's why we have broken down the weight loss into two factors. Now the first factor, that is loss with respect to the activations, or this one, would be needed for the back propagation of layer L-2, because for layer L-1 we use layer L. So for layer L-2 we will need layer L-1, the derivative with respect to layers, the derivative with respect to activations of layer L-1. So that's why instead of computing this whole thing, if we just compute this part and pass it on, to the next GPU can start computing its derivatives, while we parallelly can compute this whole thing to get derivative with respect to weights. And that's why in this paper, they say the derivative can be broken down in terms of with respect to your weights and with respect to your activations. So I'll use Z and A interchangeably. You can do the same math with respect to Z, but the point is that this can be computed first, and you can use the value of this to compute this one. So what will happen here is, naively, we were computing B1 derivative with respect to activations first, and then use that to compute with respect to weights, update the weights. Send the derivative with respect to activations to the next GPU, which does its thing. So now, instead, what this paper proposes is that we compute derivative with respect to activations, and then immediately pass that data into the next GPU so that it can start its derivative with respect to activations and not wait a whole cycle. While parallelly, we can compute the derivative with respect to weights. So that is the optimization. Of course, this is the naive implementation. You can do the same thing in the gpipe framework and so on. So they get like good, decent performance uplift in backprop, so about 1.7, which is good efficiency. So that's roughly what this paper is about. Of course, I will give the paper links in the description of this video. Moving on to the next paper. This is basically a review of how vision language models work, or rather how they're trained. This is a nice review. So just, if you got free time, just read when you're riding on a train or something. Just go through it. It's a pretty beginner friendly review of the field, like the different kind of losses, like contrastive loss, masking, generative, that are used for the different backbones, and combined backbones for vision language model, the different techniques, the different objectives, and the different backbones that are typically used. So that's a review paper. I don't think I need to specify more. Finally, this interesting paper is about how can we get transformers to do math with a high accuracy. As we know, language models struggle with math because that's not, we don't necessarily teach them for math. The large language models like GPT-4 and so on have good out-of-the-box math performances probably because they, in their pre-trained knowledge, they have pre-training, they have picked up some bits about arithmetics which make it easier for them to do 5-digit additions and so on. However, they as soon as we start doing out-of-domain stuff like 12-digit additions, they break down. So it's not really that the models are learning arithmetic. It's like they memorize certain tricks and they just do those, which kind of worked till 5-digit or 6-digit additions, but starts breaking down when you give it like 100-digit problems. And in this paper, the authors introduce a nice trick which gets them 99% accuracy. And the trick is, it's a very intuitive one, because so language models don't have an intuitive understanding of the order of numbers. So let's say I have a number 20, let's say 42, 4 is in tens place and 2 is in ones place. So that notion for digits is missing in a language model. It just sees them as tokens. So what they propose is a new position embedding in which they basically give the ordering of numbers on top of position embedding. So basically, in absolute embedding, something like 1, 2, 3, 4 plus the addition of 2 4-digit numbers would be represented like this. Just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it doesn't preserve the ordering. However, in their what they call a Baker's embedding, they give the same embeddings to the same orders. So the lowest order gets the same ending across the board. the and so on. So the highest order gets same embedding across the board and so on. So with this kind of embedding, and this makes sense, right? Because this puts all the digits on a similar footing, digits that occur at a particular order on a similar footing, or order or significance in a similar footing. And with this, they get pretty good accuracy on addition. I don't think they get very good accuracy for multiplication, because for multiplication, the order grows. With addition, if you add 2 digits, you can at max, your output will be maybe 1 more digit. Like, so if you add 2 4-digit numbers, your output could be at max 5 digits. But with multiplication, that grows exponentially, or rather, that just grows because multiplication, right? So here for multiplication, they try some technique called recurrence. Basically, they which I didn't understand completely, but it seems like they use recurrence to describe whether the different layers of decoders have different weights or not. I'm not completely sure, and they show some good results, but it's still not so good. Like so for out of domain multiplication, I don't know what out of domain here refers to. They get good accuracy, but as soon as they go beyond 100 plus digits, it's not too good. So there needs to be something else done for multiplication. Not sure what, but that was at least my quick take on this, quick skimming that I did with this paper. So it seems like for any of the mathematical tasks, we should start thinking about treating numbers, or the embedding of the position embedding of numbers separately from the position embedding of words. Yeah, so basically this was all I wanted to discuss in this video. Hopefully you liked it, and if you liked it, please like and subscribe. Thanks for watching.